Welcome back to Neural Intel. We love digging into the nitty-gritty technical details of AI tech here. And today, we are tackling one of the most maddening, hair-pulling parts of model development, the dreaded silent failure. We're going to look at a really cool tool that promises to bring some serious engineering discipline to what can often feel like total chaos. So, here's the plan. First, we're going to set the stage with a problem I'm sure you all know too well. Then, we'll look at an automated solution that's based on a pretty legendary blog post. After that, we'll get into the guts of the toolkit itself. And finally, we'll do our neural signal check and see why this is such a big deal for anyone working in a professional setting.
Okay, so let's kick things off with a problem that I swear every single one of us in this field has lost sleep over: the debugging nightmare.
You know the feeling, right? You've kicked off a big training run. The loss is going down, everything looks great, no errors, no crashes, you're feeling good. Then you go to check the actual predictions, and they're just complete nonsense, total garbage. That right there, that's the silent failure. The model looks like it's training, but really, it's learning absolutely nothing useful. Just think about it for a second. How many hours, no, how many days of engineering time and expensive compute cycles are just vaporized, tracking down these bugs that don't even throw an exception? We're talking about those super subtle issues, right? Maybe a tiny mistake in your data loader, or some weirdness in a custom layer, or even just the initialization logic. These things can totally kill convergence, and the worst part is, you might not even realize it until you're deep into a training run.
So what's the solution? Well, what if? What if we could take all that collective wisdom, all those hard-won lessons from the community about this exact problem, and turn it into a programmatic safety net, something that automatically catches these sneaky issues before they waste our time and money? And if you've been in the game for a while, you know exactly what I'm talking about. For so many of us, Andrei Karpathy's blog post, Our Recipe for Training Neural Networks, is basically required reading. It's this brilliant, super practical manual, a checklist of sanity checks you absolutely have to perform when you're building a new model, just to make sure everything's wired up correctly right from the start. Well, that's exactly what this library, Neural Net Checklist, is all about. Its entire reason for being is to take that manual, error-prone checklist that we all try our best to remember and turn it into something automated, something repeatable, something you can actually verify with code. And this is the key takeaway, really. It's about a fundamental shift in how we work. We're moving away from this manual kind of ad hoc process that, let's be honest, is super easy to forget or just mess up, and moving towards a single, clean, verifiable function call. One line of code that runs a whole suite of these critical tests for you every single time. Okay, so let's pop the hood, let's get into the toolkit itself and see what checks are actually included. What exactly is this safety net looking for? So at its core, the library gives you a set of assertions for all the most critical sanity checks. The whole idea is to make sure your model is wired up correctly before you light up those GPUs for a long, expensive training run. Let's run through the big ones.
And check out the API. This is what I really love. It's just simple. You've got a single function here designed to run all the relevant checks for a very specific model type, in this case, a causal language model. I mean, come on, this is just solid software engineering best practice being applied directly to ML development. It's beautiful.
All right, first up is a total classic. It checks your initial loss. Right at the beginning, before any training, your loss should be pretty close to what you'd get from just random guessing. So for classification, that's about the natural log of the number of classes. If your loss is way off from that, that is a huge red flag. It tells you immediately that something's probably wrong with your model's output layer or your loss function. Next up, it verifies forward batch independence. Now, what does that mean? Basically, it's making sure that each sample in your batch is its own little island. The output for one sample shouldn't be affected by any other sample in the same batch. This is a really critical check because it can catch some super sneaky bugs in things like your masking logic, positional encodings, or any custom layers you've built. Okay, for anyone working with transformers, this one is huge: causal independence. The test is actually pretty brilliant in its simplicity. It makes sure that a token's prediction only depends on the tokens that came before it, not any future ones. How? It basically feeds the model a sequence of length n, gets the outputs, then feeds it a sequence of length n plus 1, and checks if the first n outputs are exactly the same. So clever and so important. Now this next one might sound kinda obvious, but you'd be surprised how often it catches a real bug. Checking for non-zero gradients. The question is simple. Are any parts of your network accidentally detached from the loss function? If a layer's parameters have zero gradients after a backward pass, well, that means they're not getting any learning signal. They're just dead weight, not learning a thing. And finally, we get to the ultimate sanity check, the big one. Can your model even overfit to a single tiny batch of data? I mean, can it memorize it? Because think about it. If your model doesn't even have enough capacity to get to near zero loss on one little batch, there's absolutely no way it's going to learn any meaningful patterns from your entire dataset. So, yeah, this is a really neat open source tool for sure. But now it's time for our neural signal check. Let's talk about why this development really matters at a technical level, especially for enterprise deployment and any professional ML team. When you go from a manual checklist to automated assertions like this, it has 3 huge downstream effects for any serious team. Number 1, you save a ton of money. You catch these bugs early, like in your CI/CD pipeline, before they burn through expensive compute. Number 2, you enforce best practices. You're literally codifying your team's knowledge and preventing junior engineers from making the same old mistakes. And 3, you de-risk your own code. These programmatic checks give you the confidence that refactoring your code didn't silently break your model's behavior.
And that's the real takeaway here. This isn't just about debugging. It's about something much bigger. It's about finally treating model development with the same kind of engineering rigor that we've applied to traditional software for decades. We're using automated tests to build confidence, to build maintainability, and to build robustness right into the core of the development lifecycle.
So that leaves us with a really interesting question to chew on, right? This library codifies one famous set of heuristics from one blog post. But what else is out there? What other unwritten rules, what other bits of tribal knowledge about how to successfully build and train models are just waiting to be captured and automated into powerful, essential tools just like this one?
And that's our deep dive for today. If you want more explainers that get into the technical weeds of AI and ML, you know where to go. Visit our website at neuralintel.org. And of course, you can find us on Apple Podcasts, Spotify, wherever you get your podcasts. Thanks for listening.